Hi everyone. Thanks for being here. Hi Zurich. My name is Guillaume. I'm a postdoc in machine learning and optimization at EPFL, and I'm a big-time Julia enthusiast. I contribute to lots of packages in the ecosystem. And my job today is not to convince you that Julia is better than Python or that you should use Julia every time you need something. My job is to convince you that it's a fun language to learn and that you can do cool things with it. That's about the scope of what we'll be covering today. So a bit of the basics, but this is not a tutorial to learn the syntax. This is more a tutorial to get acquainted with what the language is and how it came to be. So first of all, we're going to start with the Julia story. And the Julia story starts in 2012, where a group of people at MIT got a bit greedy with programming languages. So as they said in their original blog post announcing Julia, we are MATLAB users, Lisp hackers, Pythonistas, Perl hackers. There's those of us who use Mathematica before we could grow facial hair. Of course, those who still can't grow facial hair. And we've generated more error plots than any sane person should. And then they go on to say that they love all of these languages, right? Each of them has their own specific traits that make them appealing, but we are greedy and we want more. And so they started like this, and then it took some years before they could sort of sum up their vision in 2017 in a paper that is still the reference paper for Julia. And here they explain what they wanted to fight against, basically. And they say Julia is designed to be easy and fast and questions notions generally held to be laws of nature. So when you do numerical computing, when you do scientific computing, you usually think that if you code in a high-level language, your program has to be slow. And you think that as a result of this fact, you must prototype in one language, a high-level programming language like Python. And then if you really want to get the speed, you need to get experts to rewrite your program in a lower-level language. Or, which is more or less the same, you need to use libraries that are coded in a low-level language like NumPy or PyTorch. In other words, it's supposedly impossible to get good performance purely in a high-level programming language. And so this is what they wanted to question. Is it really such an unavoidable law of nature? In 2018, the language was stable. What we mean by stable is that everything that you could do in 2018, you can still do today with the version of the language that exists. You might know that Python had a big breaking change between version 2 and version 3. So what we mean by stable is that the version will not be breaking unless we go to 2.0, which is likely never going to happen. So as they said, the language is fully baked, and now we can focus on the details. And what are the details? There's a really cool post that I like, which is called Why We Use Julia 10 Years Later. And you have about 100 testimonies of people who have used the language. And of course, they're going to tell you about the speed, about the syntax, about some nooks and crannies that they like. But what I really enjoy is, as I said here, the breadth of knowledge and kindness of spirit. Because in the end, the reason I'm having fun in this community is because there's lots of really clever people, and they're also really available to help you. Now, of course, when you use a programming language, you sometimes have to deal with compilation times. And while that may be a pleasant excuse to procrastinate, what's really nice is that in 2023, the compilation time issue was basically solved, nearly solved by this release of Julia, where basically what we call the time to first plot, that is the time you have to wait between opening your console and actually doing stuff, was divided by 10. And so this makes Julia usable on a day-to-day basis. And of course, if you're interested, every year you can go to JuliaCon. This year it's particularly appealing because it's the first time ever that it's happening in Europe. So if you're free in July, you can buy your tickets and go to Eindhoven in the Netherlands and take in all the Julia knowledge. And of course, it's not just about Julia, because it's also about what people make with Julia. Now, I'm going to tell you a little bit about the things that make me happy, and we're going to dive into really what goes on in the language. So there's a really famous developer. Her name is Frames Catherine White, and she summed it up like this. Unlike Python, the syntax for maths is actually nice, and unlike MATLAB, it's actually a usable programming language. So what we mean by nice math syntax is that you can define functions very easily like this. So this is a one-liner for Gaussian density. You just define your function phi. You can use LaTeX symbols, like if I type in here and I want to use a LaTeX symbol, first I have to find the backslash on this bloody German computer. This is here, and then I type alpha, and then I go tab, and it turns into a Greek letter. It's a small thing, but when you implement methods from a machine learning or physics paper, it's really sweet. And of course, once you have defined this, you can evaluate it. Again, I type the LaTeX symbol for this. And let's say the Gaussian density at 2 is probably this, because you know I have it memorized. You also have built-in arrays. It seems like a small thing, but in Python, every time you want to look at an array, you have to import NumPy. And here you can just define a matrix. You take its exponent. It corresponds to the exponent of matrix multiplication. By the way, does anyone recognize what's interesting about this matrix? No? The nerds in the first row? No? You're just laughing for nothing?
It's a triangular matrix.
Yeah, it's the Fibonacci numbers. You can get the Fibonacci numbers by taking the exponent of this matrix. It's actually the fastest way to compute Fibonacci numbers because it's logarithmic in complexity. And you can do more things in a really short syntax. Like here, I create a diagonal matrix and I take the exponential of that matrix, and it's all built into the language. Now, when you want to do scientific computing, more often than not, you need to do vectorized computations. Can we zoom a little? If I do Control+, nothing happens.
The control is actually...
Thank you. Perfect. So when you want to vectorize an operation, you simply need to add a dot here. So here I take the exponential and I vectorize it. So I apply it to 1, 2, and 3. And in the same way, I can vectorize this operator, which creates a pair. So I'm pairing 1 to the letter A, 2 to the letter B, etc. Among the things that might surprise you when you start Julia is that you don't have access to arbitrary large integers. In other words, when you take an integer and you raise it to a really large power, things go okay for a while, and then if the power is really large, you get a negative number, which is in a way closer to what goes on inside your computer, because numbers are stored on a fixed amount of bits, and so if you go over that, you circle back to the negative numbers. And if you want to avoid that behavior, you simply tell Julia to handle big numbers instead. So you go big, and then you have your big number, which is always satisfying. Of course, since you have built-in math, you also have built-in linear algebra. And here we get to the first part that's really different from Python, is that loops are fast. How many of you have coded something, a project for a class in Python? How many of you have had nightmares with NumPy indexing, axes, reshaping? Yeah, sounds familiar. The reason for that is because if you want your Python code to be fast, you have to use NumPy and only NumPy. You have to make every operation vectorized a la NumPy. And here what happens in Julia is that you can write two versions of, let's say, an addition between two matrices. So these are matrices of size n times n. This is the vectorized version. Forget the dollar signs. This is just an artifact of benchmarking, right? You can write the addition here. Sorry. You can write the addition of two matrices, rand and n. You can write A plus A. Okay, of course, I haven't defined n. Let me correct that. So you can define the addition of two matrices in that way. That's the vectorized way, the syntax with the dot that I showed you earlier. But you don't have to, right? You can just write a loop. You can say for every I in the indices that A and B shared, which is the same way of saying for each of the coefficients of the matrix, you do this coefficient by coefficient. And when you benchmark the two of those, you see that they take exactly the same time. That's really important. It means that if you want to write vectorized code, you can, but if you want to write loops, because loops are more readable than NumPy, axis, non, empty, reshape, etc., then you can do it as well. Yeah.
Multi-threaded?
Yes, you can actually multi-thread it. There are packages to do that, and you also have built-in multi-threading that, unlike Python, is not limited by an interpreter lock, for those who know about these kind of stuff. So this is some of the things that make me happy. Another thing that makes me very happy is abstraction. So let's say I have a function which I initially thought I would only apply to standard run-of-the-mill boring floating point numbers. This is a function that computes the square root. I don't know if you're familiar with that algorithm. It's called Héron's algorithm. It starts with the number itself, and then it applies what is essentially Newton's fixed point method until it converges to a solution. Okay, so if you apply to 2, you see that you get the square root of 2, which you're familiar with. Now, one thing you can do with Julia is you can say, what if I want to give to this function something that is not a simple number? For instance, I want to compute the derivative of my program. When you do math in undergrad, you think all you can do is compute derivatives of mathematical functions. But then you grow up and you figure out that actually, as soon as you have a function represented as computer code, you can also compute its derivative. And I'm going to show you how in 10 lines of code. The idea of differentiation is very simple. If you take a function f and you apply it to x plus a small perturbation, what you get at the first order is f of x plus the small perturbation times the derivative plus something that you can ignore. Okay, and this is basically how you compute the derivative when you want to get the formulas, right? So here what I'm doing in this cell is I'm defining a new number type, which I'm calling dual number type. And I'm saying it's going to contain the value and it's going to contain the perturbation. What I'm going to do next is I'm going to redefine all the rules of calculus to work on this number, because if I use it, if I try to multiply or add two of these numbers, without doing that, it will just fail. So what happens when I add two numbers? I'm going to add their values and I'm going to add their perturbations. What's interesting is what happens when I try to divide a number by another number of type dual. For the value itself, it's easy. I'm just going to divide a times a dot x by b dot x. And for the perturbation, I have this weird formula that reads a bit like u v prime minus u prime v over v. No, wait. How does it go? U prime v moins v prime u sur v carré. U prime v over v prime minus v prime u over v squared, right? This is the derivative of the quotient of a fraction. And so all it takes is to implement a few simple differentiation rules for your basic operations of the language. And what you get afterwards is that you can apply this function my square root to a dual number. See, here in the function my square root, all you have are multiplications, additions, and divisions. So I overloaded all of these operators, multiplication, addition, and division. And then what I get here, when I apply this to dual of 2 and 1, the first value is always the square root of 2. But the second value is the derivative of square root of 2. This is how you implement what's called automatic differentiation. And this is all made possible by the fact that I didn't force my function here to take only numbers of type float 64. That is the number that on a floating point with 64 bits. If I did that, well, of course, okay, this deserves a slight correction. This would still work, but this would fail, right? It says you can't apply my square root to something that has the following type, dual of float. Instead, I said, okay, let's leave the type free. As long as there's an object A for which I can do this type of operation, why would I not allow it to be used by my function, right? There's no need to restrict what can go on inside. And indeed, by doing so, I open the door to more generic coding. So the first example is automatic differentiation. It's okay if you didn't grasp exactly what was going on here. The following examples are a bit more simple. Now, let's take another function because it's quicker to compute with. So this is something that takes the square norm of a vector. I sum the squared absolute value over each coefficient of the vector. Okay, so let's go again. If I take a vector 1, 2, 3, the square root, the squared norm is 14. It's 1 squared plus 2 squared plus 3 squared. Now, imagine I work with very small numbers. There's a package called logarithmic numbers that allows you to store these numbers with their logarithm. And that allows you to extend the range of numbers that you can represent in your computer, because the logarithm allows you to store very, very small numbers in a way that doesn't underflow to 0. So here you can see that when I store my vector as a logarithmic float, what goes on is instead of saying this is the number 1, I'm saying this is the number exponential of 0. And here, instead of saying this is the number 2, I'm saying this is the exponential of 0.69. And when I do this, I get a result that is the exponential of 2 to the power 2.63. And of course, if I check it, I get something that's close to 14, right? I didn't add all the digits. The point is that it is still stored with the value 2.64, which is the logarithm. So the types of the inputs are preserved in the outputs. Another example, let's say you're computing stuff that has a physical unit, like a meter. You apply the square norm. What do you expect? Something that it's in meters squared. There's a package to do that. It's called unitful. I forgot to name it here. And the result is that when you plug in something that has units, even if you have complex nonlinear operations inside your function, the correct unit at the end appears. So that's really nice when you want to do dimensional analysis in physics, right? If you have a complex computation with many different physical constants, etc., you want to be sure that what you get at the end has the right unit. Another example, if you're doing experiments and your numbers have uncertainties, there's a package for that. It's called measurements. And instead of saying my number is one, my vector is 1, 2, 3, I'm adding some uncertainties to the entries of my vector. What I get at the end when I compute the square norm is a number with its uncertainty, which has been automatically propagated using the rules that you used to apply by hand in high school when you did your physics experiments. I know, I did them too. Now, there's another way of propagating uncertainty, which is called interval arithmetic. Instead of saying, because this with measurements.jl, this is basically saying a standard deviation, right? This is my number plus or minus the standard deviation. Whereas here, with interval arithmetic, you're saying, I am absolutely sure that my number lies in this interval. And so I want to be absolutely sure that the output will lie in the interval that they give to me. And so, of course, the resulting interval has to be a bit more conservative, but what you have is a mathematical guarantee that the norm of your vector is somewhere in there. This is very useful when you want to fight against floating point approximations, because you know that numbers in a computer are not exact, right? They're represented up to floating point approximation. And when you want to be protected against that, then you can use interval arithmetic. Last example, symbolic computation. Instead of using numbers, you can use just plain variables, saying abstract variables that you name v1, v2, v3, and you can build a vector with them. Let's say 1v1, 2v2, and 3v3. And then you can compute what happens when you do the norm of the vector, and you get a nice symbolic formula for that, which you can in turn differentiate symbolically as well. All of this was done with the function my_norm, which was implemented in a very simple way. And it's really, I can't stress this enough, but my_norm doesn't know about any of these fancy packages, right? It doesn't know about measurements, about interval arithmetic, about symbolics, about logarithmic numbers, etc., etc. I implemented it in one line, and the one thing that makes this work is that I remained generic in the types that I accept. If you've ever coded in Python, again, because it's the programming language I also know besides Julia, you know that for deep learning, for example, or for scientific computing, you have to pick a framework. You have to say, I'm going to work with NumPy, or I'm going to work with PyTorch, or I'm going to work with TensorFlow. And once you do that, there's no going back, right? You have to code everything within that framework. In other words, it's like if I had to commit to one of these packages, I'm going to code everything with measurement errors. I'm going to code everything with physical units. But that's not what I'm doing here. I'm coding my function independently of all of these fancy packages, and then they can take my function and do stuff with it that even I had not anticipated at first. Yeah.
Yes. So, in terms of implementation, how it differs from SQL.
Yes, I'll repeat the question. So the question is, PyTorch is a framework for deep learning, and it includes also automatic differentiation. How does it differ from this? The answer is, the flavor of automatic differentiation that I showed you is called forward mode automatic differentiation. I showed it to you because it's the simplest to explain. You basically take your mathematical Taylor expansion and you sort of code it just the way it is. In practice, for deep learning, there's another version that is called reverse mode automatic differentiation. And it exists in PyTorch. It's what PyTorch is built on. It also exists in Julia. It is much more difficult to explain, which is why I don't dive into it here. But you can also implement it using similar tricks with operator overloading. However, this is not the most efficient way of implementing it. But it's a very technical subject, so we can talk about it later if you're interested. For now, just remember that this is the simplest automatic differentiation. There's more under the hood, both in PyTorch and in Julia. And of course, if people in Zurich have questions, feel free to reach out on the question platform. Something I also like very much is this notebook. I didn't show you yet the particular aspects of the notebook I'm working on, but it's called a Pluto notebook as opposed to a Jupyter notebook. It was developed by a friend of mine called Fons to teach a class at MIT. And the idea is that who has ever worked with a Jupyter notebook? Who has ever had to do rerun all? Yes. That way you know what I'm talking about. What happens in a Jupyter notebook is that the state of your computer depends on the order in which you ran your cells. And so if you forgot to run one cell, or if you run it twice, or if you run it in the wrong order, you're messing up and there's no way to know about it. Pluto adopts a different approach in that there is no hidden state. Every cell automatically infers the parent cells that it depends on and the children cells that it influences. And as a result, you can very easily create, for instance, a slider here, which is going to influence the next cell below by changing the frequency of the sine wave. And when you update the value in a cell, it updates the plot. This seems fancy, but it's exactly the same thing as if I had done that. I can do this, or I can do that. And you see that when I update omega, it updates the underlying plot. So that's really nice for teaching. For instance, you can investigate a line of code step by step to see how it works. So here, this is the initial expression. You want to test whether this number is in this list. Okay, the syntax is very similar to Python. Just imagine that this is the exponentiation and you're good to go. So what happens here is you can execute this step by step. For instance, in the first step, I reduce the exponentiation to 4. In the second step, I perform the addition. In the third step, I materialize the list. And in the fourth step, I verified that 6 was indeed in that list. So that's another example of interactivity. And one I used very much when I taught with Pluto is you can give your students assignments. Okay, dear student, let's write a function that computes the double of the sum of two numbers. And the student is a bit struggling at first. They write something like this. And of course, you can say, you can have a test code that verifies the answer and that gives them a hint. For instance, here, you return the wrong numerical value. You could also say, here, I'm going to try to divide by 0. And here you return the wrong type because it's not a number type. And so here, of course, the right answer is this. And as soon as you plug it in, so it looks simple, but it's a really nice student experience to have access to this kind of thing. Now, I'm going to quickly conclude with two things that Julia is really good at, and then I'm going to move over and let Felix do the rest. The first thing that Julia is good at is package management. So if you're familiar with XKCD, you might have known this one. And if you're familiar with Python, then you might have lived it. So what happens with Python is that there's no one tool to install your packages. You have Conda, Anaconda, Miniconda, Mamba, Mamba Forge, and then you have all these new players like UV and stuff. And so after a few years of developing with Python, you end up with a setup that looks like this. You have your built-in Python, you have your Python from your OS, you have Anaconda, pip somewhere, maybe Homebrew, and you never know who to trust. So in Julia, as in Rust, the package manager comes with the language. It also allows you to create reproducible environments. It handles dependencies and versioning properly. In other words, you cannot install versions that are incompatible with one another, unlike pip. Pip doesn't care about your versions. Pip will set fire to your computer if it has to. And finally, it also handles unit testing and documentation. So that's really nice, right? You don't have to wonder which package management I'm going to explore next month because there's a new one in town. You always have one and it works. And the other one that perhaps is a good argument for the scientists here, the ones who are not necessarily interested in programming per se, but who are interested in getting stuff done. And the frustration in scientific computing is that you cannot do a simple code that is fast, right? That's what I told you at the beginning. If you code in Python, unless you only use libraries which are really C or C++, it's going to be very slow. This frustration has a name. It's called the two-language problem. The fact that you cannot ever code scientific stuff in one language. And it has a solution, which is called Julia. As you can check out, for instance, in these benchmarks, what's interesting with Julia is not that it's the fastest language. It's not. C is always going to be faster. And it's not the simplest language either. There are plenty of languages which are more concise. But if you take a look at the computer language benchmarks game, and if you plot the number of lines of code versus the speed of execution, what you find is that Julia sits comfortably at the bottom left corner of the graph. In other words, it's Pareto optimal in a sense. You don't get the top speed, you don't get the top concision, but you get a speed that is very, very good for the amount of lines of code that you have to write. And with that, I'm going to leave you to the capable hands of my colleague.
Okay, thanks, Guillaume. First of all, I have to reverse again the scrolling. Okay, yeah, thanks. And yeah, I'm Felix. I'm also at EPFL. I'm a PhD student. I'm in microengineering, so not quite computer science, but I studied computer science and physics. So for me, Julia is really, I'm using it daily in my work and to solve research problem around inverse modeling, which means we have some kind of physical systems. We have something we want to optimize, and then we try to model our physical system and let the optimization doing the job. And later, I'm also going to show a bit of how easy it is to set up CUDA, for example, on your computer and run simply like within 10 minutes and simple optimization, a deconvolution, in fact. But first, I want to demonstrate another thing, which actually helps because I also had a problem that I needed a radon transform, which is like a thing you have to write in a low-level language, apparently, because you need for loops. You really need tight for loops. It's like 4 nested for loops. No way you can write this in Torch or Chax or whatever. So someone had to do this in CUDA C code. But in my case, I actually just used Julia and it worked. And this is very similar to this problem here. So what happened? Yeah, so this is the Vandermonde matrix. Maybe you heard about it. It's also used in FFTs, but it has a structure that it has 1, alpha 1, and then just squared, cube, and so on and so forth. So this looks like a very structural problem. And in Python, you can use this, if you want to use this in NumPy, you have to use, you can use the numpy Vandermonde function. But if you look under the hood, it's actually implemented in C. So we can just open it, and then you will see, okay, it's, here there's some lines of code. It does some weird stuff. So it's not very quite readable. And it turns out this is not even the code. The code itself is actually implemented somewhere else. So you have to do open another file. And this varies like some kind of very abstract language. So this is not easy to read. And this is not something you want to touch yourself. It's, of course, the experts can do. But yeah, it's not something you want to do like in 5 minutes. And in Julia, doing this Vandermonde matrix is actually very easy. It's this lines of code, right? You just extract M, which is somehow the size of the matrix, and then you have one for loop where you just fill the first column of your matrix with the X, or the first column, the first rows. And then you just have another loop where you essentially multiply the number with each self to have the higher exponentiations. And this is totally fine in Julia. There is no speed drawback whatsoever. If you implement this in C, this is definitely going to be the same speed. And the funny thing is, in this case, I think it's not quite parallelizable the way it's written, but actually I wanted to tease Guillaume to show off that actually multi-threading in Julia is super easy. You just do threads.add threads. And if your for loop is independent, this works. I mean, of course, it depends on the problem if you can parallelize it, but quite often this just works. And if you have a 16-core computer, then quite often you get easily speed up 5 to 10 times. So, and that's super easy in Julia. And this is something I definitely use a lot in my work, right? If you have a problem, it's a for loop, you just sprinkle the thread and you really use, and these days, most computers have 16 or 32 cores. And in Python, multi-threading, it's a pain, right? So even NumPy, a lot of functions are not multi-threaded. Of course, if it's using the linear algebra stuff, this is multi-threaded, but quite often if you do some vector arithmetic, this is not multi-threaded. And yeah, in Julia, it's very easy. So yeah, we can call the Vandermonde matrix on a range. Otherwise, we can also do this, right? You just give it a bunch of numbers, it would do the same, but you can also do it a range. So again, very abstract. The code is just expecting an abstract vector. So it can be a range or it can be a list of numbers. Yeah, and the cool thing is this code, unlike the NumPy code, which is very specialized on floating numbers, the Julia code is very generic, right? There is not a single type annotation. Only here it's abstract vector, which means it's something like a vector, like a bunch of numbers. And very generically here we just define a 1, which is a 1 depending on the type of X. If X has units, then it would put a 1 of the corresponding units. And if it's a true or false, like a Boolean, it would put a false or a true. And so this code is very generic. You can run it again with Booleans, you can run it with the measurements errors, and you can see, yeah, it just works. You can also, yeah, whatever you want. And of course, or the funny thing is this also includes non-numerical type. So the only assumption is that the type induces a multiplicative group. And in Julia, actually, if you have 2 strings, unlike in Python, where I think it's a plus, but in Julia, it's like a multiplication. So if you multiply 2 strings, it gives you another string. It's string concatenation. So what you can do is you can just, yeah, for the sake of it, you can just call the fundamental function, and you get a big matrix, yeah, including those strings. And of course, this is not quite useful in practice, maybe, but it still shows off the composability of the very, yeah, the type agnostic function. It's just very general, and it works. And yeah, so all of the previous abstractions do not compromise efficiency. So that means you can use any number type, also the measurements number type. It's as fast as your floating number type. I mean, in some languages, having those fancy data types, you have an overhead, you lose efficiency, but in Julia, no, it's exactly the same if you measure it. And the reason is that the compiler infers the variable types very well. So what it's going to look, if it sees here, okay, this is a vector of strings, and then the compiler, if it has not been compiled yet, the compiler is analyzing all the types and is compiling a special function, the Wanda function, which is specialized on the strings, so that it can really all the way down to the atomic operations select the specialized functions for the string. And then the code is adapted to the variable types, and you have the perfect speed. So for example, if you can, yeah, look here at which just tells you which plus function is called. And if you add 2 Boolean numbers, it tells you, yeah, it's using the bool function. So we can even open it. Let's see what's going to happen. So it's going to open Julia. And what actually happens is, yeah, the plus of Boolean numbers is very simple. You simply convert the Boolean numbers to integers, apparently, and then you execute this operation. And yeah, this is Julia base, right? Just to emphasize, this is base Julia. It's kind of easy to read. It looks like Julia. There is no mixed template language or whatsoever. Yeah, we can test it for different types. For example, here, 1 + 1, it says, yeah, there's another integer function defined. Now we can open this. That probably goes down to some, yeah, to some C stuff, I think, because now we're really low already, right? We're looking at the definition of integers, how to add 2 integers, but it's still defined kind of in Julia, and then it calls, I think this is a very low level function already. Yeah, and then, yeah, it's defined for more stuff, right? So for floating numbers, it's defined, and also for arrays, right? So we can open it for arrays. So if you add 2 arrays, there's a specialized function, and the way it works, it looks a bit more difficult, but here it's just checking the size, and then here it's essentially adding the 2 functions together, the 2 arrays. And yeah, the funny thing is, if you look how many methods have been defined for plus, you can use this methods function. So you give it a function, and it gives you a list of all the definitions. Okay, this was a bad idea. It gives a list of 500 different definitions of functions. So that means, okay, now we're really
Go back to the top and very top of the table of contents.
Yeah, I think it's here somewhere, right? So what it means is that there's like over 500 differently defined plus functions, depending on the type. There's really specialized functions. What happens if you add a float 16 plus a float 32? What happens if you add an integer plus a complex float 32? What happens if you have complex number plus real number? So there's really a lot of specializations. And in some of the cases, Julia can really save a lot of work, because if you know, for example, this is also like very useful for matrices. If you have a diagonal matrix and you have a sparse matrix, you have different functions, right? So you have to distinguish, like a diagonal matrix, the addition is very, very easy compared to a full matrix where you really have to go all the entries. But if you have a diagonal matrix, you just add the diagonals together. So Julia is really optimizing or specializing on the different types, and that really can speed up things a lot. Yes, so about composability. So we talked a bit there. You've seen before that we can write generic functions, and then you can put in the measurements function and you get funky measurement errors. And so what Mose Giordano says here, yeah, the composability of the whole ecosystem, which lets you easily leverage other people's work. So in this case, we're using differential equations, which is actually one of the prime packages, let's say, in Julia. So it's probably, or most people say it's like the best differential equation package out there across all languages. So if you're into differential equations, give differential equations JL a shot. So it definitely has the best solvers around, and it solves on GPUs, and it's very, very versatile. And in this case, we just solve the pendulum equation, right? So if you're familiar with physics, so here we just define a pendulum function, and then you have du, which is like the derivative of the position, and you have the position, and then some parameters like in this case, it's the length of the pendulum and the gravitational constant, and you have a time. And in this case, you just solve the differential equation according to given by the physics. And the way it works, down here, there's just an uncertainty defined. So we have the gravitational constant, so that gravitational constant is actually not a constant. It depends where you are. For example, in Europe, people rather would use 9.81, but if you go to the US, it's 9.79. So yeah, there's a certain uncertainty, like where are you? And also you can't measure the length of your pendulum very precisely, and also initial speed and angle. But if you define all those parameters, depending on the uncertainty, and you put it into ODE problem, which is a wrapper of this differential equation, so it tells you ordinary differential equation problem, you specify all the parameters, and then you just say solve. In this case, it's using the ZIT5 solver, a relative tolerance, and then you get a solution, and then you can just use plot, which is the very general plot package, and you give it this sol.t, which is like essentially, yeah, it's an array of the solutions, but it's a measurements array because it has this fancy data type, right? And interestingly, the plot package can really take care of it, right? So you don't have to do much, and the plot package is giving you all the error bars for free. And the reason it works, I mean, in the beginning, people didn't think about there's no dependency on plots on all the differential equations and the measurements package, but instead it's relatively flawless working together because as Guillaume demonstrated before, you have the function doing specific things on what are the data types are. So in this case, as a user, it's super easy to use. You get the error bars and relatively little, few lines of codes.
What happens if you change the uncertainty value?
If I change the uncertainty value, then let's do it very big. I don't know, 5 times bigger. For example, in this case, the error also grows, right? If you have a very high uncertainty, especially for the initial speed, we can also make this a bit bigger. Then, of course, your error bar, okay, this is maybe a bit too much, but your error bars can really grow because it's, the error bars really propagate you through your physical system, right? It's a physical system, so if your initial error is kind of big, then the error accumulates and gets bigger and bigger, and at some point you're not able to predict what's going to happen, right? This is, for example, in a double pendulum, like the initial values are very critical. It's almost like a chaotic system. So if you don't know the initial values very precisely, after a while your system is completely unpredictable, which means in this case, it's still predictable, but the error bars just grow very large. And it just more or less works out of the box. So we didn't have to do anything super fancy. So easy to contribute. A lot of also I noticed it myself, right? Maybe if you studied computer science, you do some coding, but at the end of the day, you're not really a good coder. And so I had the feeling that I started to learn more coding once I actually started to use packages. And this, for me, really the first time I contributed to other packages was in Julia. And then sometimes you open pull requests. And I opened once a pull request to it's called special function. So I needed a certain type of Bessel function, which just divided by x. So I thought it's a very easy, a one-liner. So I added this one-liner and opened the pull request. And then one guy stepped up and he was saying, this is not quite correct. We have to do a Taylor expansion for small values. And the guy is actually, the guy who commented on my pull request was actually Stephen Johnson, the inventor of the FFTW library. So whenever you do FFT, it's going to use this software. And back then I was like, it was kind of amazing to talk to this guy. He's a professor at MIT, super well known in physics and computer science, and he was just guiding me through this pull request. So I spent like 2-3 days on a one-liner more or less, but we did some tests and stuff, and we did some Taylor expansions. So I really learned a lot, and for me it was a crazy experience, and really the first time I really learned also how to do proper code review and stuff. And until this day, everyone is, if you want to use this function in Julia, you're going to use this package, and everyone is using this code. So there's nothing like in Torch and TensorFlow and Chucks. Quite often you have to define things again and again, right? Image rotation is defined completely, like it's 4 times implemented in NumPy, Torch, Chuck. So every package more or less has their own implementation. But in Julia, there's a couple of big packages, like for neural networks, there's this NNLib, which is an accumulation of all the standard stuff everyone needs in neural networks, like convolutional layers, activation functions. It's just defined in this umbrella package, and all the packages downstream, they just use it. So image rotation, differentiable image rotation is in Julia only defined once. And if you want to use it, you just pull this dependency. So it feels like you don't have to do rework. You don't have to redo all the work and again and again. Yeah, so where's the catch? Julia is still considered to be a young language. I mean, right now it's 12 years since the first time it really came up, and a couple of years since version 1.0. But compared to many other languages, it's still relatively young, even younger than Rust, and even definitely younger than Python. And also packages are often, academic in nature. So there's a lot of people like me and you, which are in academia. They're doing their PhD, their postdoc, and they're developing their packages. And so sometimes you solve your problem in academia and then it's fine for you, but if another person uses it, it's not fine. So packages are often a bit rough. Documentation and maintenance can be lacking. But on the other hand, for me, it really was a great learning experience. You start to see that a package might be not quite up to date, so you start to fix it. Maybe you open a pull request, and maybe it's someday you also get the maintainer. So this is, I think actually this XKCD recently also popped up. I guess you heard when this XC backdoor on Linux happened, where like literally SSH got more or less backdoored. So it was similar like this. There was one guy maintaining a library very down in the stack, and that guy got somehow, or like there was a fishy like maintainer, and then they got backdoored, and suddenly almost the whole world collapsed. And in Julia, it can be similar, that there is some packages, like for example, CUDA, which is very critical for everyone who's doing high-speed computation, and it's essentially maintained by one guy more or less. So if I always worry, like if that guy maybe leaves Julia because he doesn't want to do it anymore, that would be a big hit for the community. And I feel like CUDA is a bit down here, but so I'm not hoping that, I'm not hoping that it's happening, and it doesn't seem like it's going to happen, but still it can be dangerous if a language is relatively young and you have a couple of people doing the heavy lifting. Deep learning is an issue right now, especially in recent years, like large language models. There's no way Julia can catch up. I mean, there's so many big players in Python, and even now also Mojo, right? There's tons of funding, billions of funding. Some people even want trillions of funding. So in the Julia world, no way there's trillions or billions of funding right now. So that's a bit sad for especially the deep learning stuff. I mean, there's a big hype, a lot of users, but in Julia, there's a couple of machine learning libraries, like Flux or Lux for common deep learning stuff. There is for scientific machine learning, where you essentially have given like a differential equation, and you don't know all parts of your differential equation, so you can plug in neural networks. So that kind of stuff is kind of good in Julia, but this classical machine learning is, especially deep learning, is not as well supported. So if you do a lot of deep learning, you might be a bit disappointed. But still, for most of the basic things, like if you do, let's say, science, and neural networks are a tool for you, and you don't rely on, like, let's say, state-of-the-art large language models, then still it's usable. So in my work, I can use it. The stuff I do, let's say convolutional layers, those kind of things, they work. That's fine. So
their field where, let's say, the go-to is Julia then.
So the go-to is the go-to is like scientific machine learning, I would say. So this is also where this differential equations package comes from. So if you really want to, if you have a physical system, and let's say a differential equation, for example, and you want to combine this with neural networks, for example, you still want to have a differential equation solver, but you want to enrich somehow your differential equation with a neural network, then those kind of things are fairly well supported. And in general, any kind of data science task, if you don't do, let's say, crazy big gigabytes of, let's say, array optimization, or maybe, I don't know, large language models, any kind of data processing is usually in Julia as good as it is in Python or R or MATLAB. So there is no big disadvantage on this side. You want to add a point?
Yeah, I just wanted to add a second ecosystem where Julia is state of the art, which is mathematical optimization. If you ever had to model a convex optimization problem or an integer optimization problem, somewhere you have an objective to maximize and some constraints to satisfy, you have packages like this in Python. But the state of the art library is called Jump, and it's in Julia, and it's universally recognized by optimization researchers. So, and in turn, you can put these optimization problems inside neural networks. So to sum up, if you have a standard run-of-the-mill neural network, PyTorch or JAX is the best choice. If you want to do something funky that is slightly out of the ordinary, when you need to tweak a few things, then Julia is better.
Okay, then yeah, installation of Julia, I guess it's not so hard. You just go on the website, julialang.org, and there's a big download button, so you can just install it. Let's skip over it. Of course, there's tons of resources also online. Maybe mention Modern Julia Workflows, which is a page Guillaume manages, right? I'm correct? So yeah, so there's a couple of workflows, and Julia is a bit different than Python, so you have to get used to it in the beginning. It might be a bit of a rough learning curve, but after a while, if you get used to the package manager and CI and all the packages, how they work, it's very easy. Yes, in many other languages, Visual Studio Code is the de facto editor right now. I personally use Vim, which also works fine. So there's no disadvantage on this side, but I'm also using heavily Pluto. So I replaced all my Jupyter. Yeah, by the way, did you know that Jupyter stands for Jupyter, for Julia, Python, and R, right? So the GU in Jupyter actually really stands for Julia. So yeah, there's also Jupyter notebooks in Julia, but recently I really switched all my work to Pluto. So Pluto for me is getting better and better. Like every month you feel like there's a new improvement, making things nicer. And yeah, for me, it's just the way to go right now.
Use it in VS Code or IDE, you can do debugging.
Yeah, debugger is a kind of a topic in Julia, so there's not a super great debugger around. So I just sprinkle show statements everywhere. That's how my debugging works. Yeah,
It's just slow.
yeah.
Okay.
Actually, it's gotten much faster.
Okay. Yeah, maybe I should give it a try. Yeah, so now I actually want to quickly show off Julia for a problem I'm usually facing in my work. And in this case, we want to do an inverse optimization problem. So this is a big optimization problem. And in this case, we want to solve something which is called deconvolution. And this is a super common phenomenon. Like if you have any imaging system, your camera, for example, your camera makes a picture of an object X. So let's say we have a picture here given, which is I just pull in a couple of dependencies. So the resolution test is a test target, which is used in, let's say, in science. So this is an image, right? And this image I want to now somehow capture with my camera. And the way a camera works, it can be described as a convolution. And a convolution is like, it's essentially drawing with a blurry brush. So you have an image and your camera is a blurry brush, so it makes the image a bit worse. So one simple way is you can say, yeah, my camera is essentially a Gaussian filter, so it makes the image a bit blurry. So what I just do size of X, and then I have my sigma. Let's choose 3. So, and this is what people call the point spread function, because it describes how blurry an image is going to be, right? So you see I have a blurry dot, and yeah, and what I want to do is now the question is, given my measurement Y, like given my measurement, which is blurry, can we recover the original image? So can we solve this inverse problem? And in linear algebra, you would just multiply with the inverse matrix, so to say, of this problem. But matrices are not capable of doing 2D images because the complexity is really bad. So in this case, what people do, they do FFT-based stuff because it's much faster, and FFT is fast Fourier transform. So maybe you learned from your calculus class that a convolution can be written. If you do the Fourier transform of a convolution, you essentially do a multiplication in Fourier space. So what we do is we are going to implement this convolution as a Fourier-based operation because it's much faster. And the way it works, what we do here, we just define our forward model, which takes X, which is some kind of input. And what I do then, I do the Fourier transform of X, maybe capital X. I multiply it with the Fourier transform of H. I don't want to explain why IFFT shift in this case, but essentially it's another Fourier transform. And then you do the inverse Fourier transform, and that gives you the convolution. And yeah, then we better take the real part because FFTs are complex and our image was real in the beginning. So I just want to do this. And now we can simply define our measurement as the forward of X. And what you see, yeah, on the left, we have the clear image. In the middle, the blurry point spread function, which makes it blurry. And on the right, we have the blurry image. And now the question is, given the blurry image, how can we come to the clear image? And in reality, of course, we also know that there's tons of noise. So let's add some noise here and maybe don't make it too strong. I have to do actually this. Then it's an array. So okay, now there's a bit of noise. It's hard to see, but there is a bit of noise. And this I want to move here. Okay, so and yeah, then in optimization, there's usually the standard way to go. you define something like a loss function. So you define, okay, I want to find an x which convolved with my point split function matches my measurements. So I want to optimize something. I want to optimize my image such that it fits to my measurements, right? So it's an inverse problem. And for that, we just define like a machine learning, like a loss function. So this thing is going to be a single number, and I'm trying to make this as good as possible. So I'm trying to find an x which fits as good as possible to my measurement. So what I just do, I define a loss function, and it's super easy. I just defined ups2, which is the pointwise application of the ups2 operation, and I simply do the forward of x minus y. So this is my loss function. And also it says here it's a very generic function. So again, this function is totally type agnostic. It works with integers, Boolean numbers, or what kind of thing you have. So in this case, then what we need else, we need a gradient, right? So if you want to do gradient-based optimization, we need a gradient to do gradient descent. So in this case, we are also going to use automatic differentiation, because of course you could define the gradient of this loss function and this FFT stuff yourself, but it's kind of cumbersome and very error prone, and it's not so easy. So luckily there's a package called Differential interface, which is a package Guillaume manages it, and this allows me to use automatic differentiation. And then I have to just follow the syntax. So this is the gradient. So it's just a bit of boilerplate. So I have to provide this is an array containing the gradient after the call. So I just give it to this function, and then I need to provide the loss function. Okay, I think it's Actually, I remember your comment from last week. So yeah, it's the other way around. It's loss G. Then I have to provide the interface. Which automatic differentiation backend do I want to use? In PyTorch, you have no choice. In PyTorch, you use whatever the language has. In this case, I can really select from a list of different ones. And in my case, I know Zygote is going to work very well. And then I just do X. And this is essentially my gradient now. And for the optimization, that's all we need. The last step is an optimizer, right? So in this case, we are going to use optim, and then we are going to use optimize. And I have to think a bit, the order.
You can open the live docs, right?
Actually, I can open the live docs, but
yeah,
they're actually not that good, huh? But I have to just think. Okay, it's first the loss. So I provide the loss, I provide the gradient. I also need an initial guess, but for the initial guess, I don't care much. So I just do an array float 32 of size of my measurement, or X. So the initial guess is very, very boring. So this is going to work. And then I need to specify my optimizer. And actually most people don't, a lot of people use Adam, and Adam might work in machine learning very well, but there's actually better optimizers out there like LBFGS. And for Adam, you need like 1,000 iterations. For LBFGS, 10 iterations is fine. So just a tip from my side. And yeah, then we just define, how many iterations do we want to do? In this case, let's try 5 iterations, and you see it's already running. Yeah, it does something. Yeah, and after like 2 seconds of running, it kind of worked well. Maybe let's do 10 seconds. But you already see, it's not quite fast, right? It takes a couple of seconds. And the reason is we are doing an optimization over 512 squared. Like we do an optimization over 250,000 parameters, which is, in school, you do optimization with the one variable, maybe Newton solver, like one variable. But here we're doing 250,000 variables, so quite a bit. So this is some heavy workload. And what you can see on the left is the original image, on the middle, the measurement, on the right, the reconstruction. And I'm gonna promise you, this is not going to be better in any other language, even though it doesn't look very great. But there is some features which you can see here on the right, which are not visible in the middle. So the optimization is definitely doing something. But yeah, as I said, it's not quite fast, right? So let's try to get it faster. And the cool thing is I pulled in here a library. It's called CUDA. So, and also it says here, I have a bit of boilerplate. It says your CUDA is functional. So what I'm doing here, I'm just now wrapping all my images in a function I defined code to, like it's togog, I call it togog. And what it does, it moves X to the GPU if my GPU works. And if there's no GPU, then it leaves it on there and leaves it on my CPU. So what I do, I just wrap this around all my array operations. So I do it here. Then it's complaining, there's some errors here. And I guess the issue is down here because the random array is also not a CUDA array yet. but I can also fix this. So I just sprinkle some togox somewhere. And now it actually is already fine. And there's only one error here because the initial guess is also not a CUDA array. But once I fix this, it should hopefully run. And if we go up here, then suddenly, instead of 5 seconds or 4 seconds, it's like running in 0.1 seconds. So for free, because my computer has a GPU, I have a CUDA GPU, the thing is much faster. And now I can easily run 50 iterations, and it just runs crazily fast. And then you also see, yeah, looks a bit ugly, the picture, right? So there's weird things going on. And this is a problem of the optimization is amplifying only noise, because I added some random noise to my image. So what I can do, I can just do a regularizer, very typical thing. And the regularizer, and a lot of people use the total variation regularizer. And what it essentially corresponds to is it's trying to say my image has to be smooth. So I can just implement this out of the box very easily here. So I do a square root. I do it like this, square root, and then I do my variable. I subtract the variable shifted by a certain amount. So I just do all the indices correctly. I do the ups2 of it, and then I essentially copy paste this. Have to get the brackets right. Seems to be all right. And then I shift the regularizer in the other direction. And zack, I have defined my regularizer. And now I define a loss function with my regularizer. And essentially, it's the old loss function from above with the x plus a certain weight factor times my regularizer. And the cool thing is, this is completely defined agnostic of CUDA, right? So it immediately, my thing here immediately ran. Okay, there is an issue because this function is actually non-differentiable. So I have to add a bit of a minus epsilon. And so adding the regularizer to my loss function makes the optimization just a bit more stable. Otherwise, the code, like else, the code is just very much the same. So on the left, the noisy image, like the noisy measurement. On the middle, the one without regularizer. And with regularizer, it looks a bit more smooth. You know, it looks not as crazy or spiky as here. And yeah, the pretty cool thing is, yeah, the whole package, like Optim, is not aware of CUDA. The automatic differentiation is not aware of CUDA. My code is not aware of CUDA, but still it runs because it's so generic. Like all those functions, they know, like the Julia, essentially the CUDA package knows how to do the ups2 of a CUDA array. The FFT essentially is using the CUDA FFT, so it knows how to do FFTs of CUDA arrays. And all those packages, they just work flawless together, even though they are not aware of CUDA. And if I would have an AMD GPU, what I could do, instead of using CUArray, where do I find it? Instead of doing CUArray here, I would do this ROC array, I think, which is then this AMD GPU, and it would run on the AMD GPU as good as or I mean, a bit different in speed, but it would run in principle. And that's a cool thing. So I don't have to change my code, but instead it runs on, I mean, PyTorch is also doing that, right? In PyTorch, you can write .CUDA and then it runs on CUDA. So it's similarly flawless. But in Julia, it's just a bit more generic. So in like if you define your loss function in Torch or in Jax or in TensorFlow, it always looks a bit different. You have to re-implement it. And in Julia, there's no difference. You can just change it. And for example, Zygote is one of the popular differentiation packages right now, but you can also change it to any of the other ones. So you could also try Enzyme, or you could also try TAP here, which is a relatively new one. So let's say Zygote would die at some point because maybe it's not quite maintained anymore. And maybe there's a new automatic differentiation package. You can just change your code by changing the backend here. So that's very convenient. And as a user, that's, yeah, it's kind of easy to use. And if you have a CUDA, you can just buy a CUDA GPU, and you can accelerate those kind of things very easily without being a CUDA expert, right? I never did any low-level CUDA programming myself, but it just works. And there's also other packages which allow you to, I mentioned the radon transform I did before, which you have to implement in for loops. There's another package which takes essentially those for loops and compiles it to CUDA code, and then this radon transform can also run on a GPU device very easily without being aware how a GPU even works. The packages are just doing everything for you. Yes, so this that's brings us to the end. So that was the last part of the talk. I can just go back here to this part. So if you need help, there's a big community. There's a Slack channel out there. Why is it always jumping? There's a Slack channel. There's a discourse which is quite active, right? There's a couple of things. So yeah, a lot of people go to Discourse once a day and see what's going on here. And there's even the maintainers of the language are posting there and helping you. So it's a very, very nice community. Don't be shy to ask. There's different threads and stuff. So in Julia, it's not Stack Overflow, but rather Discourse where people hang out. There's Zulip, there's Slack, and I don't know what else there is, but yeah, so it's very friendly and you can always just ask the people. So for me, it's a nice community, and yeah, also looking forward to the first JuliaCon in Europe in July. Yeah, so that's from our side. If there is any questions, I didn't check the webpage. Okay. So
No question. Any questions here?
No.
Yeah, I had a question about the namespace against so I saw you just run all the functions.
Yeah.
There's some conventions about
I mean, so as a user, it's totally fine to do it like this, but yeah, namespace is a problem because if I use this function here, it's kind of annoying to always find out where it's used from, right? I think the docs, they don't even tell you really where it's used, where it's coming from. That's why people try to do more these days. They do my package, and then they explicitly say, this is my function. So you can import it like this, and then it would only import the my function package, the my function. So this makes it like, let's say, I mean, if you go to, I don't know, differential equations, or let's see how Guillaume does it in this code, huh? If you go to differentiation here, and where is it?
Source.
Yeah. And if you go here, I mean, yeah, okay, you're also doing it explicitly, but a lot of package, also including myself, I'm not doing it explicitly. I have like 20 packages, and I have to keep in memory where the functions are coming from, which can be annoying. Yeah. So the better way to do is it's like this. Yeah. You want to add more? Sure.
I have a simple question. So just a clarification, what exactly makes Julia so computational efficient? Is it because it's written from scratch?
You wanna?
You can.
Yeah, so we haven't dived into it very much, but the reason behind it is that it's sort of a middle ground between interpreted and compiled languages, in that it is compiled just in time. So basically what happens is when you run a function for the first time with a new set of input types, the Julia compiler says, wait, I haven't yet compiled this Julia function to a low-level machine assembly code. And so I'm going to do it. I'm going to say, wait, you're giving me a function with new types like a string. I haven't seen that before. I'm going to compile a low-level function that is very efficient for the type string. And then all the following times that you call this function, you don't have to recompile it, and it's going to be very fast. But that's also why Julia suffered from what's called time to first plot issues, because the first time you run a function, it has to transform this high-level Julia code into low-level assembly. But then the second time is much faster. So for instance, here, it's a 2x2 matrix that my colleague very helpfully created. And so we're going to time the time it takes the first time when we call the exponential of the matrix.
So slow, huh?
Very slow.
So slow. Actually,
it's not even that slow, but the second time is much faster because we don't have to recompile it from scratch. So here, I don't think it makes that much of a difference. Oh, it does.
It did some magic stuff. I
Yeah.
think. It did some magic stuff because you could see it run. I mean, we can change the type.
You see here, there's a 10 times difference already.
But I think Julia was doing some magic stuff. Like if you see, it takes really 1-2 seconds, right? 3 seconds, 4 seconds. But I think this time statement is failing us.
Yeah. So you see here, you see the compilation, right? There's a duration that is completely incomparable to the one below, because this is the second run and this is the first run. So that's why Julia is slow on the first run, and Python users are frustrated, and then it's fast later. Yeah.
Well, question about this. Python have also used Python. That sounds similar.
I don't really know PyCache. I mean, what you could in Python, what's more comparable is like things like how's it called, Numba, and also Python is trying to add a JIT compiler. Also, Chux is very similar to Julia because they're also doing JIT compiling. What the PyCache is doing, I honestly don't know. But Python is interpreted, so every time you run it, it's just interpreting. And
I'm not sure, but I think the PyCache is a sort of pre-compiled version of some functions, right? And when you develop a Julia package, you can also say this function is going to be called very often by my user, so I'm going to pre-compile it so that they don't even suffer from the time to first plot. For instance, in the linear algebra package, if people have decided to pre-compile the exponential of a complex matrix, then these two times would be essentially equivalent because the just-in-time compilation is taken care of by the package. So it all depends on the willingness of package developers to say, this is a very often used function, I'm going to precompile it. But of course, you have to balance it with the time it takes to install and precompile the package in the first place.
I think if you, for example, if you add tab here, I think this is a package maybe not precompiled on my computer yet. And if I add it, it's like downloading the source from GitHub. And then after some while, yeah, it's fetching it. And now you would see it's installing some stuff. And now it does precompiling. So what it does, it precompiles parts of the package, which it anticipates that the user is going to use, that when you call it the first time, that you don't have to wait. So it's precompiling essentially now a bunch of functions. And when you use it the first time, you can essentially skip this precompilation.
Incidentally, you also just saw how the package manager works in Julia. So he opened the Julia console and then he just hit a specific key of the keyboard, which is the closing bracket, and he switched to what's called package mode. And then he activated a temporary environment to play around, and he just added what is the equivalent of pip install, the package called Tapia. So it's essentially a one line, and it's built into Julia. You don't have to think about which package manager you want. I think you had a question?
Yeah. About basically using any kind of data, let's say a CSV file. In Python, you have also libraries to do that. But that also what Julia is capable of doing or used for.
Yeah. So you have this library called dataframes.jl, which is essentially pandas. Or it's actually more similar to the R version, I think. Yeah. But it's very good to handle data frames, do a split, apply, combine, import from CSV, arrow, HDF. Whatever you can do in pandas, you can do in it with a slightly different syntax.
And I think actually Julia even has the fastest CSV reader on earth, right? I think there was always this competition, and I think Julia was.
I think Rust should be.
Yeah, I don't know. I think you really have to go for fastest CSV. Fastest.
I think the benchmark was called H2O, right? Yeah. So you have a benchmark of the various data frames available, and so here you see pandas is the green one, and dataframes.jl is the light blue.
Smaller is better, yeah.
And smaller is better. Panda is out of memory. Pathetic. So you see, yeah, in many benchmarks, dataframes.jl actually fares much better than pandas. And
it's just always out of memory.
Oh, it's a big panda. Yeah, so you can definitely handle data. Of course, we're going to hang around a bit for the drinks and pizza. So if you want to ask questions, but you're very scared of this whole assembly, you can just talk to us.
Other questions? Otherwise, we have go ahead.
Yeah.
Are there any big plot libraries or
plots?
Or are there derivatives of some known?
So plots is essentially an umbrella package where you can choose between different backends like GR, even PGF plots. You can choose PyPlot, you can choose Plotly, you can choose, whatever, all of those.
You can even plot in Unicode.
So there's plots is like an umbrella package, which for most of the things just work. So a lot of people just use it. And then you open Maki.
There's a pure Julia alternative, which is called Makie, and which is much faster. And it allows you to do things that are pretty sweet as well. So you can use Python matplotlib with like essentially the same syntax. There's a Julia bindings to matplotlib. Plots.jl is very similar. And then you have this one, which runs natively on the GPU as well. So it's GPU plotting.
So this is like good if you do, there's, I think, people doing crazy geographically packet, like almost satellite data, drawing some streams into some maps and stuff. So if you want to really do crazy interactive figures, which are big and take a lot of memory or which are not as easy to process, and Maki is like really, really good.
Yeah. Last one, and then we'll go have some drinks.
Yeah, can you comment more on these high-level packages? Is there like a hierarchy of packages or something? Because I don't know any.
What do you mean hierarchy?
Like plots and.
Oh, it's because it's more of it's common bindings to half a dozen different plotting backends. So it's basically using the same syntax to call matplotlib, to call a JavaScript plotting library, to call a Unicode plotting library. And so you can all do this with the same syntax. So it's essentially a collection that you can call with the same function names and same arguments.
I mean, there's
like inbuilt hierarchy of libraries in Julia.
no, that's not like this. It's like, I think it just recently it evolved that more and more people somehow they realize there's a bunch of packages doing the same, like also Guillaume, like with the differentiation package, that there's 10 different differentiation libraries. And then now someone thought, yeah, maybe let's try to combine them together. The same is actually for optimization. There's 10 different optimization library. Then someone thought, yeah, let's do an optimization where we use one interface to use all of them. And yeah, that's why I think, because it makes it's so easy to develop a library, which is high speed and very efficient, that people thought, yeah, instead of using this library, I make my own. But of course, that makes it a bit clustered or fragmented. So that's why it maybe sometimes makes sense to make one umbrella package to merge them together.
But usually what you have is not umbrella packages, but rather umbrella organizations. So there's a thing on GitHub called organizations where several users can collaborate on a series of packages. And usually when you're interested in a specific topic, there's one or two Julia organizations which do the trick. So for instance, I'm interested in optimization. So there's the Jump ecosystem and there's the Julia Smooth optimizers or Julia non-convex. If you're interested in scientific machine learning, like Felix said, it's SciML. If you're interested in machine learning, you can check out Julia Stats for the classic stuff, and then Julia AI or Flux for the more deep learning oriented. So usually you go to an organization, and if we do things right, there's one organization. But of course, it's sort of an organic community, right? It's not like Python where you have big companies pouring millions of dollars into one specific package. It sort of arises naturally, and so sometimes there's fights. Sometimes there's two people implementing the same stuff at different times, and so we try to collaborate. Sometimes it works, sometimes it doesn't. But more of the time, I would say the collaboration experience is rather pleasant, and it's how you get nerd sniped, basically. You start coding Julia like Felix did, and then you do your first contribution to a package, and then all of a sudden you become a maintainer or co-maintainer of a small package, and then one day you say, I'm going to create my own thing. And because it's Julia, you can create your own thing with a few months of experience and have it be the fastest thing in the universe, basically. So it feels nice developing in Julia. That's really the message that we want you to keep in mind.
There's one question on your side. In which language is the compiler of Julia written?
I think it's in Julia. Yeah.
I mean, Julia and LLVM. So Julia essentially is using LLVM as a backend, as many other languages now do, like Jax or also Mojo. So it's using LLVM, but on top of LLVM, there sits mostly Julia code. And you can open the Julia main repo, which is Julia Lang, I guess, and then Julia. And there's a bit of C. And there's a bit of femtoList, but also they got rid of it. So most of it is really Julia. There's a bit of C, C++, and then a bit of LLVM binding. So at the end of the day, most of the stuff is really written in Julia.
And an interesting consequence of that is what's called meta programming, is the fact that you can analyze Julia code using Julia code. And you can sort of use Julia to modify its own code. And that gives you a lot of power once you go a bit deeper into the trenches to do very dangerous and unholy stuff. But that's for later.
Let's switch to the quiz and let's give a round of applause for Felix and Guillaume.
You want to connect your computer? Yeah.